Have you ever looked up at the night sky and wondered where it all came from? The Big Bang theory suggests our universe began as an incredibly hot, dense point, smaller than an atom. Around 13.8 billion years ago, this singularity began to expand rapidly. Imagine a balloon with dots drawn on its surface. As you inflate the balloon, the dots move farther apart, just like galaxies in our expanding universe. This expansion continues to this day, and it's one of the most compelling pieces of evidence supporting the Big Bang theory. The Big Bang theory isn't just a story, it's a scientific model supported by a wealth of observational evidence. By studying the light from distant galaxies, the cosmic microwave background radiation, and the abundance of light elements, scientists have pieced together a compelling narrative of our universe's history. This narrative begins with the Big Bang. Imagine the universe in its infancy, just a fraction of a second after the Big Bang. At this point, the universe was an unimaginably hot and dense soup of elementary particles. As the universe expanded, it cooled, allowing for the formation of more complex structures. Within the first second, quarks combined to form protons and neutrons. As the universe continued to expand and cool, electrons were eventually captured by protons and neutrons, forming the first atoms. This process, known as recombination, occurred roughly 380,000 years after the Big Bang. Before recombination, the universe was opaque to light. After recombination, the universe became transparent. This first light from the early universe is still detectable today as the cosmic microwave background radiation. The intense heat and pressure of the Big Bang created the perfect conditions for a remarkable cosmic kitchen. In this high-energy environment, hydrogen and helium were cooked up in a process known as Big Bang nucleosynthesis. Protons and neutrons collided at incredible speeds, fusing together and releasing tremendous amounts of energy. The first few minutes after the Big Bang were a flurry of nuclear reactions, forming helium and trace amounts of lithium and beryllium. By applying our understanding of nuclear physics to the early universe, physicists can predict the relative abundances of light elements. These predictions closely match the observed abundances, providing strong evidence for the Big Bang theory. After the formation of the first atoms, the universe entered a period known as the Dark Ages. This era, lasting hundreds of millions of years, was characterized by the absence of stars and galaxies. Gravity, the architect of the cosmos, was already at work, shaping the universe's destiny. Over time, tiny fluctuations in the density of matter began to grow under the pull of gravity, forming vast clouds of gas. Within these gas clouds, gravity caused the clouds to collapse and heat up, igniting the first stars. These first stars produced heavy elements like carbon, oxygen, and iron, eventually exploding as supernovae. These stellar explosions triggered the formation of more stars, illuminating the universe and ending the Dark Ages. Imagine a faint afterglow, a whisper of light, permeating the universe from every direction. This faint glow, known as the cosmic microwave background, CMB radiation, is the oldest light we can detect. The CMB is a faint but incredibly uniform glow of microwave radiation that fills the entire universe. Discovered accidentally in 1964 by Arno Penzias and Robert Wilson, it revolutionized our understanding of the early universe. The CMB is the afterglow of the Big Bang, the cooled-down remnant of the intense heat and radiation that filled the early universe. When the universe was young, light couldn't travel freely due to constant scattering by free electrons. Around 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with protons, forming neutral hydrogen atoms. The CMB is the snapshot of the universe at this moment of recombination, a baby picture of the cosmos. In the 1920s, astronomer Edwin Hubble discovered that most distant galaxies were moving away from us, indicating that the universe is expanding. Imagine baking a loaf of raisin bread. As the bread bakes and expands, the raisins move farther apart, just like galaxies in our expanding universe. The expansion of the universe isn't like an explosion, it's the fabric of space-time itself that's stretching. This discovery was a major triumph for the Big Bang theory, providing direct observational evidence that the universe was once much smaller and denser. In the 1990s, astronomers found that the expansion of the universe was accelerating, driven by a mysterious force called dark energy. Dark energy makes up roughly 68% of the total energy density of the universe, yet we know very little about its nature. If dark energy continues to drive the accelerated expansion, galaxies will eventually become so far apart that we won't be able to see them from Earth. The universe will become a cold, dark, and lonely place.